In section 5.3, we'll be discussing related rates. So often you are going to see related rates problems on the AP exam. So you'll be given the rate that something is changing and asked to find another rate of change. So in order to do this, you need to differentiate both sides of an equation, and that will be implicitly with respect to time. The time won't always be obvious that it's there. It's kind of embedded in the variables. These might seem tricky at first, but they will follow the same pattern. So before we get to a full-on related rates problem, we're going to practice implicitly differentiating some formulas with respect to time. So here we have A equals 4 pi r squared. That is the surface area of a sphere. You're not required to know that formula. But what we want to do is take the derivative of all of these terms with respect to time. So that means our t is kind of acting like our x variable, and both A and r are actually functions of time. That just means they're changing with respect to time. So when you see those variables, you're thinking about them as functions, not just like a single variable. So when I take the derivative of a, that is just dA dt, and we'll write it this way instead of a prime, just to emphasize that we're taking the derivative with respect to time. On the right side, we have 4 pi r squared. That derivative would be 8 pi r, and then times dr dt, because I have to take the derivative of r as well, because it is not just equal to time. So essentially, when I take these derivatives, every time I will have to multiply by the derivative of that variable, the dr dt. Number 2, we have v equals 4/3 pi r cubed. This is the formula for volume of a sphere. If I take the derivative of volume is just dv dt. Here, the derivative of 4/3 pi r cubed is 4 pi r squared, and then times dr dt. You'll notice here that the derivative of volume without the dr dt actually gives you the area, the surface area of a sphere. So that's a fun trick. That also works for area and circumference of a circle. Number 3, volume is pi r squared times h. Now, because there is a times h there, we've got two different variables. We'll have to use the product rule on the right side. So the derivative of volume, dv dt, equals the derivative of the first part, 2 pi r, but don't forget the dr dt, and then times h, plus pi r squared, and then the derivative of h is dh dt. Don't worry about simplifying that. You can simplify once you actually evaluate at some different points. So when we're solving a related rates problem, we're going to do essentially these same steps every time. So first we're going to draw a sketch. So a lot of times these are story problems, so drawing a sketch, trying to figure out the geometric representation is going to help us out. Then we'll set up an equation relating all of the relevant quantities. So figuring out what the variables are, using the information given in the problem. Number 3, we'll differentiate implicitly on both sides with respect to time. That's just like what we did up here. Then we'll evaluate or substitute in values for all known quantities and derivatives. We always do that after we take the derivative, so this step is really important. It's after step 3. Then we'll solve for the remaining rate, and then we have to make sure to smile because we just did a challenging related rates problem. As you read these problems, it will be important for you to pick out important information in the problem. I would recommend that you highlight or underline things as you go. So number 1, an oil tanker has an accident on a bridge and spills out at a rate of 20 cubic feet per minute. So I'm going to highlight the rate and the actual, what the rate is. Whenever I see that word rate, that's going to be important to me. Suppose that the oil spreads out into the water in a circle, so that will be important, with a thickness of 1/10 of an inch, or 1/120th of a foot. Determine the rate at which the radius of the spill is increasing when the radius equals 500 feet. So I know I just underlined a lot, but there's quite a bit there that I want to take in. So in number 1, we're going to draw a sketch. Now, it tells me that it's a circle with a thickness. That really means it's a squash cylinder. So I've got a circle here with some thickness, so just like a cylinder essentially. It tells me that my radius is equal to 500 feet. It's not always 500, it's just 500 in this case. So I'm going to go ahead and label that. So I'm going to call that R. My radius disappeared. Also, it tells me that my height is 1/120th of a foot. I'm going to use that so that all my units are the same. I should have put feet up here on my radius as well. The other information that was given to me is that I have this oil that's spilling out at a rate of 20 cubic feet per minute. And so I need to try to write that as a rate. If you're not sure what that is, pay attention to the units. I see cubic feet per minute. The cubic feet tells me that this has to do with volume. So volume is measured in cubic units, and then the per time means it's the rate of change of volume. So what I can say is that dV dt, the rate of change of the volume, is 20 cubic feet per minute. For these other variables, h, the height, the oil is spreading at a constant height, so that means its rate of change of height is 0. What I'm looking for, I'm determining the rate at which the radius is increasing. So I'm looking for dr dt. I always find this part to be important to actually write out what am I looking for so I can keep track of it as I work out my problem. So number 2, I want to set up an equation relating all relevant quantities. So in this case, what I have going on, I have volume, I have height, I have radius, so I want the volume of a cylinder. Now this formula is on your Stuff You Must Know cold sheet, but it's not something, well actually it may not be on your Stuff You Must Know cold sheet because you don't actually have to have it memorized, but it's something that would be given to you on the AP test. So things like area, circumference, perimeter of shapes, those are things you should be able to figure out. Surface area and volume are usually given. So volume of a cylinder is pi r squared h. So essentially area of a circle, pi r squared times the height. So that's step 2. Step 3 is to differentiate implicitly on both sides. So the derivative of volume is dV dt. The derivative of the pi r squared h. This was up number 3 up above, or part C. I don't remember what you called it. 2 pi r dr dt times h plus pi r squared times dh dt. So again, I'm using product rule there. Now, after I've taken the derivative, and only after I've taken the derivative, I'll go ahead and evaluate with what I know. So I know the dV dt is 20. That was given to me. I know my radius is 500 at this moment. Dr dt is what I'm trying to figure out. I know my height is 1/120. Plus pi times 500 squared times 0 for dH dt. And now what's nice about that multiplying by 0 is that whole second part is just going to cancel out. That's all just equal to 0. So what I really have is just 20 equals 2 pi times 500 times 1/120 times dr dt. And so I can simplify that. I'm going to go ahead. So step 5, I'm solving for the remaining rate. I'm trying to find dr dt. I'm going to simplify this right side. So this is 1,000 pi over 120, which would be, that would be 25 pi over 3 times dr dt. And so then when I'm solving for dr dt, I'm essentially just going to multiply by the reciprocal of this fraction. So I'd have 60 over 25 pi equals dr dt. And then I can simplify that, but you do want to make sure your rate has units at the end. And so I'm going to say dr dt. I can simplify that a little bit. I can divide each of those by 5. 12 over 5 pi. Now this was the rate of change of the radius. The radius was in feet, so this is going to be feet per minute, per my time in the problem. And don't forget your smiley face because we're happy to have solved this problem. Number 2, a 10-foot ladder leans against the side of a building. The top of the ladder begins to slide down the wall at the rate of 2 feet per second. How fast is the bottom of the ladder sliding away from the wall? The top of the ladder is 8 feet off the ground. So let's go ahead and draw this. We have a wall and the ground. We have a ladder. So this should be a right triangle problem. We're assuming that the wall is perpendicular to the ground. We know our ladder is 10 feet. It's sliding down the wall at a rate of 2 feet per second. And we want to know how fast it's sliding away. We know the top of the ladder is 8 feet off the ground. So let's go ahead and label some variables here. You could use whatever letters you want. I'm going to use X and Y. So I know that I'm looking at when my Y is equal to 8, but it's not always 8. I do know that I'm sliding down the wall at a rate of 2 feet per second. So for dy dt, it's not just 2 though, it's actually negative 2 feet per second. Because I'm sliding down the wall, my distance is decreasing. My x then is increasing. So my horizontal distance would be increasing if I'm sliding down the wall. What I'm trying to find is dx dt. How fast I'm sliding away from the wall. Now, I don't know what my x is, but I could figure out what x is if I need to. We'll see if we need to. We can come back to it. But what we want to think about now, that was step 1. Step 2 is we have to come up with an equation that relates these variables. So right now I have the sides of a triangle. So that means I'm going to use, for a right triangle, Pythagorean theorem. So x squared plus y squared equals 10 squared. And so when I go to take the derivative then, the derivative of x squared is 2x dx dt. The derivative of y squared is 2y dy dt. And the derivative of 10 squared is just 0 because it's a constant. So I will need to plug in for x, dx dt is what I'm finding, y and dy dt. So let's come back over here and solve for x. We're just going to use the same equation, Pythagorean theorem here. X squared plus 8 squared equals 10 squared. So x squared plus 64 equals 100. So x squared is 36 and x is 6. So then step 4, I'm going to go ahead and plug in 2 times 6 dx dt is what I'm trying to solve for. My y is 8. My dy dt is negative 2. So those negatives, a lot of times, you're going to have to infer in the problem. So just pay attention to that. Equals 0. Step 5, let's go ahead and solve. 12 dx dt minus 32 is equal to 0. So 12 dx dt is equal to 32. Dx dt is equal to 32 over 12. That simplifies to 8 over 3. And then don't forget our units. So x would have been measured in feet. Our time is in seconds, so it's feet per second. Number 3, if a snowball melts so that its surface area decreases, so that decreases is going to be important, at a rate of 1 square centimeter per minute, we want to find the rate at which the diameter decreases when the diameter is 10 centimeters. So let's draw a picture here of a snowball. So we're going to assume that's a spherical snowball. I'm just going to make it look a little more three-dimensional here. And so it tells me the surface area is decreasing. So that's ds dt. You can call it a if you want. I'm just going to call it s. It's decreasing, so I know that's going to be negative 1 centimeter squared per minute. What it's asking me for is the derivative of the diameter with respect to time. We know my diameter is 10. So the formula that we'll use here, because we're given the surface area, is the surface area of a sphere formula. That is 4 pi r squared. Now what you'll notice is that this has the radius given to you, not the diameter. So we have to find some connection between those. We know that our diameter is equal to 2 times our radius. So in other words, our radius is half of our diameter. So we need to rewrite this equation before we take the derivative so that this is in terms of the variables that we have here. So if I take my diameter over 2 and I square it, that means I have times my diameter squared over 4, which actually just means I have pi times my diameter squared. So that will give me the surface area of my sphere. I have to do that before I take the derivative because the derivative of the diameter, the rate of change of the diameter is not exactly proportional to the rate of change of the radius. So I do need to do that before I take the derivative. So now I'm taking the derivative of this equation, s equals pi d squared. So ds dt is equal to 2 pi d times dd dt. Then I can plug in. So ds dt is -1. My diameter was 10. And then the rate of change of diameter is what I'm trying to find. So now I solve. So I have -1 over 20 pi equals my rate of change of diameter. And really, I just need to, I'm going to rewrite it this way, negative pi over 20. And then my units, this is diameter, which would be measured in centimeters per minute. Always make sure you go back up and read the units in the problem. It might not be what you assume it is.